Let me ask you something. What if I told you that most of your failed experiments, they aren't bad luck. They're self-inflicted wounds. Not because you're a bad scientist or because your idea was wrong from the start. Nope, it's because of these tiny, almost invisible habits. The small decisions you make every single day in the lab that quietly, methodically destroy your own data. Today, we're pulling back the curtain on these silent saboteurs that turn promising research into just meaningless noise.
Okay, let's just start with a number that should honestly stop you in your tracks. 85%. That's the estimated slice of global research funding. We're talking billions with a B that gets wasted every year on studies that are fundamentally flawed. Flawed in how they're designed, how they're run, or how they're reported. And look, this isn't just about the money. It's about your time, your effort, and frankly, the credibility of science itself.
And this quote, this just nails the heart of the problem, right? It all starts with one tiny decision. You see something's a little off, a control that's acting weird, a baseline that's drifted, and you have to make a choice. Pushing forward in that moment, telling yourself it's probably fine, is basically a declaration that getting it done is more important than getting it right. It's a small compromise that just invalidates everything that comes after it. Now, let's be really clear here. This massive waste we're talking about, it isn't typically because of some mustache-twirling villain committing outright fraud. The real culprit is way more sneaky. It's the honest mistakes, it's the hidden biases we all have, it's those ingrained lab habits that get passed down for years without anyone ever asking, hey, why do we do it this way? These are the self-inflicted wounds that sabotage our work long before we even think about analyzing a single data point.
So where does the rot set in? Well, a lot of the time, the fate of your experiment is sealed before you even pick up a pipette. We're talking about the fundamental design flaws, the cracks in the foundation that pretty much guarantee the whole thing is going to crumble later. So let's look at the mistakes you can make before you even start.
The very first choice you make is about your approach. Are you starting with a clear, focused, and, this is key, falsifiable hypothesis, a real question that guides every single move you make? Or are you data dredging? Just collecting a ton of data on everything you can think of and then sifting through it, hoping a significant pattern just magically appears? That second path, my friend, is a minefield for false positives. It's basically a recipe for discovering things that are just random chance. And that brings us to this absolutely critical concept, statistical power. The easiest way to think about it is like this. It's the sensitivity of your experiment. If there's a real effect out there to be found, what's the probability that your study is actually equipped to see it? And studies with low power are one of the biggest reasons we get false negatives. We miss real discoveries. The accepted minimum is usually around 80%, but you would be shocked how many studies fall way, way short of that, dooming themselves from the get-go. So you have to ask yourself this question: what are you looking through? An underpowered study is like trying to discover a new planet with a foggy pair of glasses. I mean, sure, you might get lucky, but you are way more likely to miss it completely, or worse, mistake a smudge on the lens for a planet. A high-powered study, on the other hand, is like a finely tuned telescope. It gives you the clarity you need to see what's really there. All right, so let's move away from the planning phase and into the trenches. We're at the bench now, where a whole new set of saboteurs are just waiting to mess things up. These are the physical errors, the tiny slips in technique that can pile up and compound into catastrophic failures. A classic. I call this the cold reagent trap. We've all been there. You're in a hurry, the protocol says use at room temperature, but you grab that buffer straight from the 4-degree fridge. You've just thrown a massive, unrecorded variable into your experiment. Cold liquids are more viscous, they pipette differently, and they completely change reaction speeds. Thermal equilibration isn't just a friendly suggestion, it is an absolute prerequisite for getting data you can trust. And how about the one tool we use more than anything else? The pipette. Look, if you aren't pre-wetting your tip, especially with volatile liquids like ethanol or acetone, your first measurement is basically a lie. Why? Because the air inside the tip has to get humidified by the solvent first, and that little bit of evaporation throws your volume off. The fix takes, 3 seconds? Aspirate and dispense back into your source a few times. This tiny little habit is the difference between precision and pure guesswork. Okay, this next one is huge. Ever run half your samples on a Friday and the other half on Monday? If so, you've just fallen victim to batch effect blindness. You didn't just split up the work. You introduced a giant confounding variable, the day itself. The temperature might be different, the humidity, maybe even the lot number on your reagents.
You can't just statistically remove the Monday effect later. If you absolutely can't run everything at once, you have to use a randomized block design. No excuses.
And finally, a word on mixing. It can feel so satisfying to just blast a sample on the vortexer and watch it swirl, right? But for a lot of samples, like big, beautiful, high molecular weight DNA or delicate protein complexes, you're not mixing it, you're shredding it. You are literally destroying the very molecules you're trying to measure. So the lesson here is simple. Be a surgeon. Use gentle, precise inversion. Don't be a blender.
All right, so let's say we've done everything right. We've collected our data, we've avoided all the traps at the bench. We're safe now, right? Nope. We're now entering what might be the most dangerous phase of all, the analysis. This is where our own biases can trick us into making the data say whatever we want it to say. This is where data can start to tell some pretty convincing lies.
And that brings us to the world of p-hacking. The simplest way to describe it, it's torturing the data until it confesses. It's about finding creative ways to analyze your data, maybe excluding a few outliers here, running a different test there, until you can push your p-value just below that magic 0.05 threshold. Now, it's not always malicious. It often comes from a real belief that your hypothesis is right. But it's one of the biggest drivers of the reproducibility crisis in science. Now, p-hacking has an equally shady cousin named harking. That stands for hypothesizing after the results are known. Here's the difference. With p-hacking, you keep your hypothesis and you just keep changing the analysis until you get the result you want. With harking, you run a ton of analyses, find some surprising correlation, and then you go back and write the introduction to your paper as if you brilliantly predicted that exact outcome all along. It's like shooting an arrow at a barn wall and then drawing a bullseye around wherever it landed. So what does p-hacking actually look like in the wild? Well, the strategies are depressingly common. You've got optional stopping, which is when you keep peeking at your data as it comes in and you stop the experiment the second it crosses that magic p-value line. Or there's selective reporting, measuring 10 different things but only publishing the 2 that were significant. Or my favorite, casually excluding inconvenient outliers that are messing up your beautiful trend line. All of these are ways of gaming the system to get a result that probably isn't real. And if you don't think these little tricks matter, just look at this. This graph shows how dangerous peaking is. In a normal experiment, you accept a 5% chance of a false positive. That's just part of the deal. But some amazing simulations have shown that if you continuously peek at your results and stop as soon as you hit significance, your false positive rate doesn't just go up a little, it skyrockets from 5% to over 55%. You've just increased your chances of being dead wrong by more than tenfold. It's staggering. Okay, wow. We've just walked through a complete minefield of mistakes. And I know it might feel a little daunting, maybe even a little discouraging, but here's the good news. Avoiding these traps isn't about being some kind of scientific genius. It's about having a system. It's about building a bulletproof protocol that protects you from your own biases and your own bad habits. So here's what that looks like. It's actually pretty simple. First, pre-register your hypothesis and your entire analysis plan. This basically locks you in. It prevents you from p-hacking or harking later. Second, randomize everything you possibly can. The order you run samples, where they sit in the plate reader, everything. Third, document every single deviation. If someone can't perfectly replicate your work just from reading your notes, you didn't do science. You performed a magic trick. Fourth, blind your analysis. If you don't know which sample is the treatment and which is the control, your expectations can't subconsciously influence the result. And finally, use reporting guidelines to make sure your work is transparent and fully reproducible. So I want to leave you with this one question to think about. The next time you get that exciting result, that really clean-looking data, just pause and ask yourself, is this discovery real? Have I built a robust, truly bulletproof case for it? Or have I just gotten really, really good at decorating noise? The answer to that question, well, that's what separates a fleeting finding from lasting science.